Welcome to the deep dive. Today, you're joining us for a really fascinating journey, not through ancient history, like the name might suggest, but actually deep into distributed computing.
Right. Sounds maybe a bit dry, but it's not.
No, not at all. We're tackling the Byzantine Generals Problem, and honestly, don't let that name put you off. It's really more like a logic puzzle.
A very important one, though.
Definitely. How do you get a team to agree on something crucial when, some of them might be actively working against you?
That's the core of it. Think about it like this. Any system where different parts need to cooperate reliably,
Okay.
even if some of those parts are, well, broken, or worse, malicious, it pops up everywhere in tech.
So let's paint the picture. Imagine you've got these Byzantine army divisions,
Right.
each led by a general surrounding an enemy city. They need to decide, attack or retreat.
And it has to be unanimous. Everyone does the same thing.
Exactly. Because if some attack and some retreat, you can imagine.
Recipe for disaster.
Yeah.
Total failure.
And the real challenge, the core difficulty here, is that these generals are miles apart. They can only communicate using messengers.
And that's where the trouble starts.
Yeah.
Messengers aren't exactly secure.
Right. Some generals might be traitors. Or the messengers themselves could lie or get intercepted, have the message changed.
Yeah. Total lack of trust in the communication channel, basically.
So the loyal generals, the good guys, need a foolproof way to agree despite all this potential sabotage.
And any plan they come up with has to meet two really key conditions.
Okay, what are they?
First, all the loyal generals have to decide on the exact same plan. Unanimity among the good guys.
Makes sense.
Second, if the commander, the one giving the first order, is actually loyal, then all the loyal generals must follow that specific order.
Got it. So consistency and obedience to a loyal leader.
Exactly. And our sources point to basically two ways to try and achieve this, two main strategies.
Okay.
One uses what are called oral messages. Think of it as just talking. No proof of who said what.
Okay, like hearsay.
Pretty much. The other uses signed messages, which adds a layer of authentication.
Like a signature you can verify.
Precisely. And we're going to dig into both of these, see how they work and where they succeed or fail.
And this isn't just theoretical, right? This problem actually matters in the real world.
Oh, absolutely. It's a model for reliability in computer systems. Think distributed databases.
Where different computers need to agree on data.
Exactly. Or fault-tolerant systems, systems designed to keep working even if parts break down.
Right.
Even secure computing, where multiple parties need to calculate something together without revealing their secrets. The Byzantine Generals Problem helps us understand the fundamentals.
Okay, fascinating. So let's start with the first approach. Oral messages, the sort of Wild West version.
Yeah, Wild West is a good way to put it. With oral messages, the big limitation is you can relay a message, sure, but you can't prove who originally sent it. Or if it's been tampered with along the way. Anyone can claim anything.
And that lack of proof, it causes problems.
Big problems, especially with small numbers. The sources show it's actually impossible to guarantee agreement if you have just 3 generals, and one of them might be a traitor.
Only 3? Wow. How does that work? Or not work, I guess.
Okay, picture this first scenario. Figure 1 in the source. The commander is loyal. Good guy.
Right.
They order attack and send that message to Lieutenant 1 and Lieutenant 2.
Okay.
But Lieutenant 2 is a traitor. So Lieutenant 2 tells Lieutenant 1, hey, the commander said retreat.
So L1 hears attack from the commander, but retreat from L2.
Exactly. And L1, hearing directly from the loyal commander, probably attacks. But L2, the traitor, obviously retreats.
No agreement. Disaster.
Yep. Now flip it. Scenario 2, figure 2. This time the commander is the traitor.
Okay, the boss is bad.
Right. The commander tells Lieutenant 1 attack, but tells Lieutenant 2 retreat.
Sneaky.
Very. Now, the lieutenants, remember, can't verify the commander's message, so they might talk to each other.
Trying to figure out what's going on.
Yeah. So L1 tells L2, I heard attack. L2 tells L1, I heard retreat.
So now L1 has heard attack from the commander and retreat from L2.
And L2 has heard retreat from the commander and attack from L1.
Each one has one attack and one retreat. Total confusion.
Exactly. They're stuck. They can't reliably decide. These simple cases show that with 3 generals and 1 traitor, using only oral messages, you just can't guarantee agreement.
Wow. Pretty stark.
It leads to a really important general rule that the source points out.
Okay.
For a system with n total generals and potential traitors, to reach agreement using only oral messages, you absolutely need n to be greater than 3 times m.
And 3 meter. So More than 2/3 have to be loyal.
Precisely. You need a significant majority of good actors to overcome the potential disruption for the bad ones if you can't verify messages.
That makes intuitive sense. If there are too many potential liars, the truth gets drowned out.
Yeah, and this isn't just abstract. Think about building, say, a fault-tolerant system with 5 computers. This rule tells you it can only handle one faulty computer if you're just relying on simple message passing.
Only 1 out of 5. That doesn't sound very robust.
It isn't. Which is why this limitation was a big driver for finding better solutions. But, which is why this limitation was a big driver for finding better solutions. But, the source does give an algorithm that works when N3 meter. It's called OM.
Algorithm oral message. Okay, how does OM manage it?
It's recursive, which is kind of neat. First, the commander sends their order attack or retreat to all the lieutenants.
It's a standard start.
Then, and here's the clever part, each lieutenant temporarily acts like a commander.
Okay.
They take the value they got from the original commander, or maybe a default value like retreat if they got nothing,
Right.
and they send that value to all the other lieutenants. So everyone is relaying what they heard.
So information gets spread around multiple times through multiple paths.
Exactly. After all this message passing, each lieutenant looks at all the messages they've received, the original one for the commander, plus all the relayed ones from the other lieutenants.
And then?
They apply a majority function. Whatever value appears most often, attack or retreat, that's the decision they make.
Majority rules. So even if a traitor relays a false message.
Hopefully enough loyal lieutenants relayed the correct message that the majority vote still comes out right for the other loyal guys.
Okay, that sounds plausible.
The source has a diagram, figure 3, showing this with no traitors but maybe one unreliable lieutenant. You can see the loyal ones still get the right order if the commander's loyal.
And what if the commander is the traitor? Figure 4, I guess.
Yep. In that case, the commander might send conflicting orders like attack to L1 and retreat to L2.
Right.
When the loyal lieutenants relay these, they'll share this conflicting info. L1 will say, I heard attack. L2 will say, I heard retreat.
So they still get mixed signals.
They do initially, but because they all share what they heard and then all apply the majority function to the same set of relayed messages, or nearly the same, allowing for the traitor's lies, they should still land on the same outcome.
So maybe they don't follow the traitor's commander's specific wish, but they achieve agreement among themselves.
Exactly. They satisfy that crucial first condition. All loyal generals decide on the same plan, even if it's just a default, like retreat, which is better than chaos.
Okay. So the bottom line for oral messages, it can work, but you need way more good guys than bad guys, that N3 meter rule. And OM gives a way to do it with lots of communication and majority voting.
That's a good summary.
Now let's shift gears. Signed messages. This sounds like it should fix a lot of problems.
It really does. Signed messages are a game changer. The key idea is cryptography.
Digital signatures.
Exactly. Think of it like an unforgeable seal.
Right.
If a message says it's from the commander and has their valid signature, the lieutenants can be, highly confident it's genuine.
Okay, so you can trust the source of the message now.
And that it hasn't been altered. A traitor could still send a message, maybe even try to forward a fake one, but they can't forge a loyal general's signature.
So you can just ignore messages with invalid or missing signatures from loyal generals.
Pretty much, or at least treat them with extreme suspicion. This ability to authenticate really strengthens the system.
How does it change those conditions we talked about? IC1 and IC2.
Right, so IC1 is a loyal lieutenant obeys an order if it's verifiably signed by the commander. Straightforward.
Makes sense.
IC2 adds, if the commander is loyal, then every loyal lieutenant will obey that signed order. It gives a stronger guarantee of following the leader if the leader is trustworthy.
Okay. So with signatures providing this trust, how many traitors can the system handle now? Does that N3 mural rule still apply?
Nope. That's the big improvement. With signed messages, you can achieve agreement with any number of traitors.
Any number. Seriously?
Almost, as long as the total number of generals, N, is at least M plus 2. So NM plus 2.
N greater than or equal to M plus 2? Wow, that's way better than N greater than 3 meter. You just need at least 2 non-traitors besides the potential traitors themselves.
Essentially, yes. It's a much more resilient setup. You don't need that overwhelming majority of loyalists anymore.
That's huge. So how does the algorithm, SMM, I assume, work?
Algorithm signed message, yeah. It starts similarly. The commander signs their order and sends it to every lieutenant.
Okay.
When a lieutenant gets it, first step. Verify the signature. Is it really from the commander?
Crucial check.
If it's valid, and they haven't acted yet, they store the order. Then they add their own signature to the message, basically endorsing it, and forward this doubly signed message to all the other lieutenants.
Ah, so you get a chain of verifiable signatures. Commander signed this, then Lieutenant 1 signed that they received it, and so on.
Precisely. It builds a verifiable audit trail for the message.
Okay.
Each lieutenant keeps collecting these signed messages. If they receive an order that traces back to a valid signature from the commander, directly or relayed, and they haven't decided yet, they adopt that order.
What if they somehow get conflicting signed orders? Like if a traitor manages to trick someone, though you said forging is hard.
Forging should be computationally infeasible with good crypto. But maybe a traitor could forward old valid orders or try other tricks. The core idea, though, is that the genuine, correctly signed order from the commander will propagate through the network of loyal generals. Because they can verify its authenticity, they will eventually converge on that order.
So the valid signature acts like an undeniable piece of evidence that cuts through the noise.
Exactly. One traitor. The traitor lieutenant might try to send a fake message, maybe even claim it's from the commander.
But it won't have the real signature.
Right. Or they try to forward a different order claiming it's the commander's. The loyal lieutenants checking the signature chain will spot the mismatch. They'll ultimately follow the message with the commander's authentic signature.
Makes sense. The signature is the key.
It really is. And these ideas, they're not just for this simple setup. The source mentions things like missing communication paths or regular graphs.
More complex networks.
Yeah. Think of a computer network where not everyone is directly connected to everyone else.
Right, more realistic.
If the network is sufficiently connected, like if every node has at least a certain number of neighbors, what they call a p-regular graph, then these kinds of algorithms, OMM and SMM, can be adapted.
So even with some broken connections or nodes, if the overall network structure is strong enough, you can still achieve agreement.
That's the idea.
Right.
But it still relies on that connectivity. And there's a trade-off, right?
With the signed messages.
Yeah. They're much more robust against traitors, require fewer loyal participants overall. But they depend entirely on having a secure, reliable signature scheme. Managing cryptographic keys, ensuring signatures are verified correctly, that adds its own complexity and overhead to the system.
So no free lunch. Oral messages are simpler but need way more loyalty. Signed messages are more robust but need crypto infrastructure.
You got it.
So this whole Byzantine Generals thing, it really just boils down to how you build reliable systems from potentially unreliable parts.
Absolutely. And the source notes how these concepts directly influence practical techniques we use today. Redundancy, just having multiple components doing the same job. If one fails, others carry on.
Makes sense, like airplanes having multiple engines.
Kinda, yeah. And majority voting, like we saw in OMM. If you have several computers calculate something and most of them agree on the answer, you trust that answer even if one computer gives garbage.
Ah, okay. So these ideas are fundamental to fault tolerance.
Definitely. It shows that even if some components fail or are malicious, the whole system can still work correctly if it's designed right, using these kinds of agreement protocols.
It's actually kind of comforting, knowing that systems can be designed to withstand internal failures or attacks.
Yeah, the elegance of the problem is how it captures that complex challenge in such a clear analogy.
Okay, so let's quickly recap this deep dive. We dug into the Byzantine Generals Problem, the challenge of getting agreement in distributed systems with potential traitors. We saw two main approaches: oral messages, which work only if you have a strong majority of loyal participants, that N3 mirror rule.
Right, lots of communication, majority voting.
And signed messages, which use crypto signatures, much more resilient to traitors only needing NOMN+2, but requiring that signature infrastructure.
Yep, verifiable authenticity is key there.
And these aren't just abstract puzzles. They give fundamental insights into distributed consensus, which is crucial for everything from operating systems to blockchain.
Essential concepts in modern computing.
It really makes you think, though, beyond just computers. You know, these ideas of redundancy, verifying information sources, building consensus, how do they apply in our daily lives?
That's a great point. Trust and reliable information are critical everywhere.
Yeah, think about different ways we communicate, face-to-face versus, say, an anonymous online comment section.
Huge difference in built-in reliability and verification, right?
Totally. One feels much more resilient to, well, to traitors spreading misinformation than the other. It's kind of the same problem, just on a human scale.
It really is. It all comes back to how you establish trust and agreement when communication itself might be flawed.
The fascinating puzzle indeed. Thanks for joining us for this deep dive. Maybe take a moment to think about where you see these struggles for agreement and trust playing out and how the communication methods involved make it easier or harder to find the truth.